Thank you. So, as the title says, this is the case for bringing file support to OpenMP. And let's get to it. We'll first start with the motivation. I think now I'll spend more time on this one, since the last paper didn't introduce motivation for IO in OpenMP. And then I'll show some pragmas and an API that we're proposing to handle IO in OpenMP. Again, we don't have front-end support for the pragmas. That's a proposal, an idea, a discussion for how pragmas should support that. But we do implement an API and run some tests on it. That's why we have an experimental results section. And then we end with the conclusions. So why IO support in OpenMP? We all know the drill. HPC is heterogeneous, the memory hierarchy is deep, it's pretty hard, complex latency, complex topology. That's how it goes. But the HPC storage is also heterogeneous and distributed and can vary from one system to the other, and it's pretty hard to get consistent performance in your system. And not only that, the I/O bottleneck can intensify with scale. Usually, the storage part is the lowest part of your system. So if you're trying to fit everything in the GPU and it doesn't fit there, so part of it will be in the RAM. If it doesn't fit the RAM, it's gonna be on the disk, and that's gonna be the lowest of all. So you have to be considerate of that. And we also know that OpenMP evolved over time to cover some changes in the HPC ecosystem. For example, introducing the tasking model and introducing the offloading model. But as for today, there is no support for file I/O. And here we argue that if we will let the runtime be aware of I/O tasks, it can get up to 1.4 times speed up in a simple toy workload that I argue is representative of HPC kernels. So the I/O stack today in HPC, we have many software layers to cover the working system. So let's say we have an application, could be a simulation, anything that's pretty heavy, and it has to write to the disk, be it because your matrix doesn't fit in memory, be it because you're gonna save checkpoint status over time. Probably you're gonna use some high-level I/O library to give structure to the data and perform some optimizations. In turn, that library will interact with some middleware. For example, Romeo, that is the MPIO most used middleware, that talks to lower level POSIX IO. And sometimes that's not even the end of the story. Maybe that's not even handled by the kernel directly. We can have a parallel file system. That's what usually we have in HPC that manages those IO operations through the POSIX IO interface. And then it has a distributed system of metadata and data blocks in parallel on a separated network. That's not the case for every system, but that's how complex it can get. Of course, we have many optimizations that happen in I/O. We have caching, batching, perfection. We can coalesce small access to improve the throughput. But where in the stack does it happen? The same optimization can appear many, many times. Let's say we want to do caching. Your application knows that it's going to access the same buffer many, many times, and you can bufferize it to the main memory. But when you open a file through the POSIX.io, the Linux kernel is going to create a page cache and buffer it in memory as well. So it's not it's an isolated view. And when the kernel is doing the page cache, it doesn't know anything about the flow of execution of your application. So you miss some information there, you repeat some optimizations, and we miss many opportunities for this cross-layer coordination because we don't have a global view of the disk usage across the stack. So our proposal is let's let the runtime manage the I/O. So the runtime knows the application structure and know the contention on the underlying system. And I will argue that we should integrate that with the task dependency graph. We'll propose some I/O clauses like I/O read and I/O write and a list of buffers. That way, the runtime knows the tasks that use I/O and the regions of the files that each task reads. And then the runtime cares for all those optimizations, being aware of the system and the application structure. So it can prefetch, throttle the access to avoid oversubscription, and coalesce small access into larger ones. And to do that, we provide to the OpenMP library this libmp file backend diagnostic layer. So just as an example, here we have the user code, let's say the user calls OMP file open. And we want that to be backend agnostic, so that call is going to go through libompfile.so. That's going to give you an opaque pointer to reference that file. We have two advantages here. The first is that the libomp library only has to deal with this single interface. And the second thing is that we can have different backend implementations to provide the file access. So here is a quick view of our, oh, it's too clear, but I think it's readable. So now this API from libomp file provides those functions that the user can use to manipulate files. We can use OMP file period or OMP file open. Here we are creating a file type. So we are specifying that this file contains a vector with this base OMP float 64. We took inspiration on some of the MPIO interface on getting this information from the file structure, because this allows us to, for example, know how many bytes we have to offset for a given interval of the array. And then we can use the IO clause to specify file regions. But that's on the next page. So for now, we are creating a vector type of OMP float 64 and opening a file matrix type and opening two other files, M, X, and Y. And here's an example of using the IO clauses. Again, we don't have the front-end implementation for this. Every time that when I show you the benchmarks, that's with the API calls written by hand. But the idea here is that with IO regions in the clauses, that we have an IO region here, the runtime is aware of every IO operation and can do optimizations based on that. So here we have an IO read, and I'm telling the runtime that this kernel here is going to read this section of this matrix and this section of this array. And we imagine that it could be integrated with, for example, a target no wait in reduction. So we are doing reduction over this variable with data read from this file. And now the runtime has this amount of computation and communication that it can manage and overlap. Here is a smaller kernel with the task graph on the side. This is the one that I'm going to show you the benchmark on. So it's a simpler one, but it still has some perfection opportunities that only appear because the runtime is aware of the IO operations and know that they are IO operations. So here we're doing element-wise multiplication over two arrays, over three arrays actually, and saving the scalar result. So we saw this before, OMP file open, we declare the type, opening the files, and here we have our multiplication kernels. So we're creating a task. It reads the array F, the array V, and the array W. It does the element-wise multiplication and has a dependency on R1. And then we have another task that reads another array called U and take the results from the previous task and multiply them and accumulate over R2. So this is our task dependency graph. We are opening two files that are marked in red, multiplying element-wise, and then opening a third file and multiplying them element-wise. Here we see that there is this perfection opportunity that appears because this read operation has no incoming dependencies. So it can run as soon as it is discovered. But there's one additional thing here. Notice, if the runtime was to say, okay, there is no dependency here, no dependency here, no dependency here, I can issue those three reads in parallel. That could be bad for performance because you would be oversubscribing the IO system if you have a regular hard disk. So issuing many reads in parallel can hurt performance. So not only the runtime knows that this can be launched early, it knows not to launch while those reads are running. It can wait for those to finish, and then while the computation is happening, it launches this read in parallel. So this is not only an IO task, but a runtime that is aware that this task is not computation intensive, but rather hard disk access intensive. Let's go to our experimental setup. Again, we're using Spinner for the parameter sweep, graph plot, and confidence interval calculation, a tool that we made in-house. And that is what we use to provide the artifacts for the article. We used server blade that has a hard disk and an NVMe. The specific model is in the paper, if that is important. We run two benchmarks. One is the IOR benchmark, is a disk HPC benchmark. We use that to check if our agnostic layer introduces any relevant latencies. And then this baked vector multiply that I just saw you with a perfection opportunity. We run all on a single node, but I'm reporting the MPH version because IOR uses MPI to launch the benchmarking process. So you have to have that installed to launch it, but it's all single node. So first, the library overhead. We are running with small block sizes because that's where the overhead would appear. And we are checking the number of IO operations per second using different backends for IWOMP file backends against regular POSIX calls. So we just implemented a new backend for the IOR benchmark. And we have two tests here. One, change the number of threads issuing parallel reads, and one is parallel writes. And then IOR number of operations per second, varying the block size. We have two cases here that MPIO backend and IOU ring backends have a bigger overhead because you have a small penalty for startup times here. For example, in IOU ring, you have to create the buffers and allocate them using syscall, so that takes a while. But overall, they are pretty close. And the takeaway here is that our agnostic layer for IO operations doesn't add any big penalty. Regarding disk, every data point that we put here is started with cold caches. So we ask the sysadmins to provide a command to clean the page cache before the experiment starts. But each point accesses the disk many, many times. So inside each run, the application is benefiting from the page cache, but each point starts with cold caches. Here we have another test that is, what if I have a parallel for region with a varying number of threads, and inside this parallel region, I'm writing to a file. I don't have overlaps, so no race condition. I'm writing to different portions of the file. If I increase my number of threads to bigger numbers, I start to oversubscribe the IO system and I start to lose performance. So for the POSIX dumb implementation, just a parallel for region with pure write inside, with 32 threads, the performance actually degrades. But when we have our runtime managed IO, it knows to throttle the concurrency, and then we can keep the performance as we increase the number of threads. There is still a gap here. There is some implementation problems that we didn't fix yet. So we still lose to regular POSIX IO in this write case, but it's just some implementation details. The takeaway here is that a runtime that manages IO can prevent oversubscribing automatically. And again, there's the argument for portability because you write a code for a system with 4 nodes, it's fast on the IO side. And you move to a better system, it gets slower because now you're oversubscribing the IO system. This is the benchmark for the vector multiply with IO tests. Here we have the size of the vector. Here we have the end-to-end execution time. The bars are the execution time. I'll talk about the line later. As we increase the size of the vector, we can start getting some speed up to almost 1.4 times, because we are prefetching part of the array, making the last task starts faster, reducing the overall compute time. The line here helps us visualize the gains opportunity that we have in the application. This is the ratio of time that the application is blocked waiting for IO. So there's no computation to run. We are just waiting for data to come from the disk. So if you see here in the smaller case, so let's see this point here, that we have the smallest vector input. Almost 100% of the time we spend waiting for IO. So there's not much computation that you can overlap with I/O to gain some speed up. Here on the larger side, the naive implementation without I/O prefetching, there's roughly 50% of the time you're waiting for I/O. So you have 50% of the time of computation happening and 50% of the time waiting for I/O. You have some margin to overlap the two and gain some performance. And that's the gain that we have when we enable automatically perfection with I/O tasks. Here's the same experiment, but from using a faster storage system, that's the NVMe. Now we start gaining performance even for smaller sizes. And that's because since our storage system is faster, the proportion, the ratio of time that we spend in computation relative to I/O is bigger now because the I/O is faster. So our prefetching show gains earlier. So even from our smallest cases, there is at least 1.1 speed up gains and goes up to 1.41 times. And again, that results that we just saw was for this test graph. And I mean, we argue that that's for a simple case with just a vector element-wise multiplication, but that pattern can appear inside other computations, so it's reasonable to imagine that it will show benefits in other kernels as well. So the conclusions, we present a backend agnostic library that doesn't add much to overhead and provides a common interface for the OpenMP runtime to interact to. We also show that I/O information lets the runtime do prefetching and throttling, like the runtime is informed of the I/O operations. And also that the task graph scheduling with explicit I/O tasks leads to better performance. Again, it's not only treating I/O as an independent task with its dependencies, but the runtime is aware that this is an I/O operation and can make scheduling decisions based on that. As future work, we believe there is a natural extension of this to run this on multiple nodes and leverage those optimization techniques from parallel file systems automatically from the runtime side. And from that, we are going to rely on the MPI proxy plugin. We can also think about accelerator-aware I/O paths. For example, NVIDIA has GPU Direct, I think, where you can move data directly from the disk to the GPU memory without staging through the main memory. And we can achieve that. The runtime can do that automatically if it's aware of the accelerators, the characteristics of the accelerators, and the I/O operations. We can go further and think about cloud and object storage endpoints and map that to our library. Let's say you have a large data set that is on a server. You don't want to bring the whole data and operate on it. You can just have a common, like mark as a dependencies, the array of the file that this task is going to interact, and let the runtime manage that. And then some poor runtime guy figure it out. And also have some limitations. For example, almost all I/O systems has some sort of hints interface where you can give optional information about the execution. We have to think about that for our I/O interface. We also need a better error model for that because things can go wrong on the I/O side. And also this one is, I think, needs some thought that we presented the I/O clause as something that maps part of the file to the memory that the task is going to access. So this task is going to access this slice of the array. But as for now, OpenMP, as far as I know, doesn't support partial overlap of the memory regions. They can overlap entirely or not overlap at all. But with files, it's common for those small overlaps to happen. So that's something that we have to think about in I/O programs. And that's it. Thank you for your attention.
Questions? Was that no? Okay, I have one for you.
Okay.
So when you do the I/O clause, does it mean that when you schedule the task for execution, you do the I/O? When that is done, you do the task? Or is it that you actually kind of separate out some sort of I/O task that you schedule independently and concurrently to the main execution that is going on.
More or less the second case. So
Okay.
it's just like if, since we have an IO here, it's as if we have another independent task here that can be
Okay.
scheduled to bring this. But it's a special task because the runtime knows it's an IO task. So it knows not to oversubscribe the disk with all the available IO tasks if you have too many, because that could hurt performance.
Okay. Thank you. Questions? I can fire up another one.
Please.
So you presented the chart where your IO bandwidth stayed almost constant because you didn't oversubscribe system. Does that also reduce latency for IO in total because you keep the bandwidth high, or did you compare if oversubscribing actually keeps the latency down even though bandwidth goes down a little bit?
I mean the latency for it to start, I think it stays the same, but we only measure the average of the bandwidth after transferring a whole, I think it was 64 megabyte, right? Something like that.
Okay. Okay, thank you. So.
I have a question. Thank you for the talk. I'm not sure I quite get on that because you mentioned earlier, but why is IOU indicating less performance than the other?
This IO ring here.
Yes.
So just to be clear, that's IO ring as a backend for our libomp file interface, right? So if anything, I'm also, if you have a bigger delay there, it also has to do with our own library starting it up. Because libomp file provides to the libomp library POSIX like IO operations. So file open, pread, prewrite, and so on.
Also blocking operations.
Yes, so that doesn't fit exactly the model for IO ring.
Yeah, right. Because they would expect IO ring to get the most performance because that's why they were introducing the Linux kernel. So wait, that also means in the execution model, the semantic of the clause IO read write. So does that mean that the thread that executes the task blocks at the end, for instance, if it writes the letter, blocks at the end of executing the task, writing the file?
Blocks writing the file. You can issue an async write through the interface here.
Okay, so another thread will take care.
Yeah, it just keep on the internally to libmap file. It don't have to block on the return to it. It has the async functions interface, similar to Linux async IO, which you can set a callback for when it finishes.
Okay, thank you for everything.
And also this experiment here, we are paying, like for each point, we're paying the price of registering the IO ring buffer, which takes a small while because you have to do a syscall for the kernel to say, okay, this section of memory is where you can write the IO requests, and this is where I will write the result of the IO requests. So you have to register, you have to alloc and register that buffer. While with the POSIX interface, you don't have to do that. You just talk to the file through one syscall. So you have the startup time of the registering the ring buffer.
Okay.
Which again is more on our backend than on IO ring itself.
Rodrigo, can you explain again the results you see in NVM?
In NVM, yes. So here, so just to recap, so this is this application running, right? And the orange part is when we have let the runtime prefetch this data here. The bar is the execution time, and the line is the time the application stay blocked, waiting for IO without any computation to run. From NVMe, starting on this, for this size of vector, this number of elements, we can see that we spend this amount of time, this ratio of time waiting for IO. Since we don't have prefetching in this red line case, the rest of the time is doing computation. So we have this opportunity to overlap the two. because take a look at the figure. This is computation, this is computation, and this is I/O. This is some I/O that you cannot overlap with computation because the computation here only starts after this I/O is ready. And so you have a limited opportunity for overlapping, and that's what this line shows. Like the difference here is the amount of I/O that we could overlap with computation and thus gain some performance. Yeah, because like reading the array here is also like we read the full array before starting. We could go as far as think about pipelining it somehow, but I don't know how would that fit the model.